Good.
Yep, we can see your screen.
All right. Well, thank you here for having me. It's great to kind of get everybody together who's kind of using this equipment for a lot of different tools. I'm excited. It's great to see what other people are using it for and the applications that they're taking these kind of incredible technology to. Today, I want to talk to you a little bit about a new project we've been working on in my lab at Villanova University. We're a primarily undergraduate institution, so our teams are much smaller. And this is a project we've been working on for the past year. And kind of to start from the beginning, structural phases of a material are just a different arrangement of atoms. So in the 2D materials community, we love to talk about carbon. Graphene is a huge area of research. And so when a compound is made of a single atom, we call these polymorphic crystals. If we have more than one atom making up material like boron nitride, this is usually termed allotropes. And with carbon, we can see that there can be different crystal structures or a lack of crystal structure. So you can have amorphous carbons, coal, you can have graphite, which is a layered structure, or diamond, which is a three-dimensional structure. And just by, these are three materials we're very familiar with. We can see that just by eye, the materials look very different while being the same atom. Their mechanical properties change drastically, the electrical properties, and so do the optical properties. And so we'd like to, understand this in a way that we can use them in nanomaterials and nanoelectronics in particular. So in nature, these different structural phases can form based on the thermodynamic conditions under which they grow. We know diamond is formed under high pressure. There could be doping materials around it that form different structures, or relative amounts of the ingredients for these materials. And that can be the same as growing things in a lab, but it would be great if we could have some sort of local control over these parameters where we see a kind of a GIF here of a laser engraving on some material where it changes at least the color for this purpose of certain regions that we can pattern. And what we would aim to do is use a beam of electrons to selectively transform small regions into a different structural phase. And this has great implications for practical applications for future electronics, and also from interesting physical phenomena, how electrons behave in small confined structures, quantum dots, quantum wires. And ideally here, we would be able to take a material that would be electrically insulating and write either semiconducting or metallic patterns inside that material. And we don't necessarily have a material that does insulating to metal by exposure to electrons, but we have this 2D material, molybdenum bisulfide, where it lives in this family of transition metal Dichalcogenides, or TMDs for short, where we have in a single monolayer, we have a layer of transition metal atoms that are surrounded by a layer on either side of these chalconigide atoms. And this layered structure where we have the strong intralayer bonds, but weak interlayer van der Waals bonds is kind of a shared property among all van der Waals materials. And generally in this class of materials, they have a honeycomb structure, much like graphene, where we have these unit cells containing a single transition metal atom and two chalconigide atoms. And these TMDs are very often semiconductors. MOS2 is one of the more common ones, these TMDs. In its natural phase, it's an intrinsic semiconductor, which means it has an energy gap that separates its conduction band and valence band. And in this 2H structural phase, we have the sulfur atoms on the upper layer exactly mirroring the position of the sulfur atoms in the lower layer. And the band gap is around 1 eV, so it's not a great insulator, but it does have other stable phases that can be induced. If we just slide one of these sulfur layers into the holes in these honeycomb structures, you can see here one layer has been moved over, so now we have purple indicating the lower sulfur plane and orange indicating the upper sulfur plane. In this configuration, is known as its 1T configuration, MOS2 becomes metallic. So the gap disappears, and we have metallic behavior just from a small sliding of one of these atomic layers to the side. For definitions that'll become clearer as we discuss studying this transition, the work function of a material is the minimum energy you need to remove an electron. This is, from the famous photoelectric effect with which Einstein won his Nobel Prize, even though we think of him as a relativity pioneer. This is really what he explained with quantum theory. The light has to have a certain energy to get an electron out of the material. And so this just says the highest energy electron, which is defined by the Fermi energy. How much energy do we need to get that out of this potential well of the material? So we're going to be measuring this, and we're going to be studying this transition when we shine a focus beam of electrons on this material. And so I first want to give some motivation of why this transition might be induced by pumping electrons into the system. But it's also a phenomenon that's been observed. This is TEM data of a monolayer MOS2 with increasing electron doses as we go from right to left. And so we can see in the TEM data these kind of same coding of orange and purple regions, where in the A here, the undosed MOS2 monolayer, we don't really see much purple. But as we dose electrons in that layer of MOS2, or the sulfur atoms slide out of the way, the TEM gets sensitive to this underlayer of sulfur atoms. And you can see at some point we've formed this triangle of this 1T region in kind of a bulk 2H material, where now we're seeing kind of those bottom sulfur atoms interfere with the TEM, the transmission of the electrons. In this measurement, they're actually doing this dosing at this spot as well as imaging at the same time. It's all done in situ. This was done in about 2014. But to get back to the why we can transition from a semiconductor to a metal, we can think of it when we're in this 2H phase. We have this empty conduction band and a filled valence band. When we shine this electron beam on the material, we're inserting electrons at a high energy. They slow down and kind of come to rest in the material, and they fall down in energy to the lowest available energy state, which would be at first the bottom of the conduction band. So at first, we're just starting to fill up that conduction band, and the work function here would actually decrease because this Fermi level is rising up. And it's just driven by Pauli exclusion principle that the electrons can't just fall down to the valence band. They have to take the lowest energy unoccupied state. At some point, we can think of all inserting these electrons as keeping them at higher and higher energies. And eventually we have a lot of electrons donated to this material. And even though the atomic lattice is in its happiest energy state, its lowest energy state, we now have these really high energy electrons, these hot electrons, and they would like to come down in energy and lose this potential. So what the whole crystal can do is give up some favorability in the electronic or the atomic configuration in order to get these electrons down to a lower energy state. We can think of it like filling up a water tower. Eventually, if it's not structurally sound, the water tower will collapse and allow the water to drop down to a lower state. And this is what would happen in a phase transition, that the crystal has gone to a higher energy state, like a metastable state, but the entire system of ions and electrons has now come to its its full minimum in energy. And so this is the energetic incentive for the phase transition. And we want to study this by measuring the work function of this as we dose with higher and higher doses of electrons. If we want to think of this in terms of what to expect for the change in work function as we increase our electron dose, we'll define a change in work function being how much did the work function change relative to the natural state of the 2H. So we're always comparing it to the material we start out with. As we saw at first, we're just filling the conduction band. So this work function will decrease because the electron levels are rising and rising. And the slope of this line would be proportional to the density of states in the system. And so for a semiconductor, that's generally given proportional to its effective mass. So if you were using another material other than MOS2, this work function change would be maybe less or more steep here. But at some point, as we said, you've got a ton of electrons at high energy. They're going to want to reconfigure the atomic structure. The phase transition happens to the 1T phase. And so we get a flipping of the sign of the change in work function. We've now gone below the work function we had when we were in the 2H phase. And here we can also think of further dosing after this phase transition is just donating electrons to this system. But typically the density of states for a metal is incredibly large. So if we see any like change in as we increase the dose, it's going to be a very small change here. The definition of a metal is there's plenty of electronic states at the Fermi level. So we shouldn't see much of a plateau here or much of a decrease in the plateau, but it could be there if we're sensitive enough. If you want to think of this from another perspective, you can think of the level you're filling the electrons up to. The Fermi level will slowly increase as we're filling the conduction band, and then it will drop off and then maybe start to creep back up as we donate more electrons to the metal. The way we pattern our MOS2 is through a standard 50 kV electron beam lithography system, which operates, we have an electron source that's focused down to a very small spot size, and it'll expose a region, move to a next point, expose again, and move forward and forward at some pitch between these spots of length L. And so we can define the amount of time we expose a region to with a constant current of electrons. And so a point dose is defined by the beam current times the time we dwell on each position. And then the area dose would take into account the spacing between those points. How many electrons are we donating to this material per nanometer squared, for example? At each point, so we kind of zoom in on one spot here, this phase transition actually nucleates from a point and expands outward with the more dwell time that we let on the surface. And so we can control the size of these spots with how long we're shooting this beam at a particular spot. And so what eventually happens is, just like we saw in that atomic data, we get these little triangular islands of metal in a 2H material. And depending on the application or the intent of what you want to study, we can kind of vary the parameters here of how big of a metallic island do we want to have, how far do they want to be separated. And for our purposes, we want to, these, I should say, the size of this region of 1T that we can obtain is about 75% of our beam diameter. So we're really drawing patterns that are smaller than the diameter of our electron beam. And that electron beam is usually around a few nanometers, 1 to 3 nanometers. So we can grow these islands up to about 2.5 nanometers in side length. We can control this. We can control the maximum size we can grow by using a larger spot, which is typically a higher beam current. It's harder to focus a high current beam. And then we can set the number of points in the field, basically taking an SEM image and breaking it down pixel by pixel. And so we can dwell at a certain time on each pixel and create islands in size that we want. If we pick a spot size that's smaller than the pitch between points, we would get isolated islands. So here's each time the beam stops and exposes for time t, and this would produce these blue islands of the metallic phase in an ocean of semiconductor. However, for this work, we want to study the work function as we increase the dose. So what we're going to do is make our spot size much larger than the pitch. We're going to have a lot of overlap with our beams, and this creates very metallic focused surface coverage. Generally, you'll have maybe some leftover semiconducting islands, quantum dots in this metallic background. But here we're aiming for mostly 1T phase. We're going to get a specific size coverage. If this was a 1 micron box, we'd have a lot of points in there, and we'd like to have it be all metallic. Typically for this study, we kind of studied a ratio of about 3. So the pitch was about 1/3 of the spot size. Originally, our intuition was if you want to see when something becomes a metal, you might want to do transport measurements. Just watch the resistivity drop as you dose it more. MOS2 is notoriously hard to contact. You form Schottky barriers when you deposit a metal on there, and there's certain ways to get around that. But this was kind of the approach we took from the beginning. And you can see here we took pairs of leads and we exposed a little strip in between those leads to the electron beam, and then we're going to look at the resistivity of the sections as a function of dosing to see if we could confirm we were getting this metallic phase. And pretty quickly we kind of learned of the Kelvin probe force microscopy, and we're interested in observing the work function change this material. And you can see the results here where you can see our gold contacts here and the 2H MOS2. And then if we look at and there's nothing special between these gold leads, but when we looked into the work function map, we saw that the undosed region had a fixed, more or less constant work function, and the work function greatly increased when we exposed it to the beam of electrons. And like we said, if it was just doping and filling the conduction band, we would expect the work function to decrease. So we already had some intuition that the phase transition was occurring here. You can see also that the work function of the 1T region is very close to the work function of gold. And so it might at least qualitatively argue that it is a metal phase. And when we decided to look at this in more detail, what we did is we took a flake of MOS2, exfoliated on a silicon dioxide wafer, and we patterned 1 by 1 micron boxes in a 7 by 3 array, where we had a small dose down here of about 1 femtocoulomb per spot, up to 3 orders of magnitude higher at the largest dose, kind of increasing here. And we saw a couple interesting things right away. One is that we actually saw, in contrast to this slide here, that there was a slight variation in the height profile, the topography in our dosed regions, which we didn't exactly expect at all. If it was happening in the MOS2, we would expect it to be some sort of change in the inner layer interactions, which we didn't think would happen by just a layer sliding. We didn't have some major atomic reconstruction. that we suspected. And we also saw that the work function kind of evolved in not a monotonic way, which might be expected. You can see here in the work function, the darker regions are a low work function and the bright regions are a high work function. So we see a significant increase in the work function material. And we plotted these as a function of dose, like going from 1 to 1,000 femtocoulombs per each point. And the black dots here show the change in the topography. And so at low doses, we see a decrease in the height. We have some constriction in the material, and it kind of plateaus around 3 nanometer divots in our material. We also see something in the work function that increases to more than 100 MeV. So it's a significant change in the work function. And we were then interested in how does this variation in the height scale with the flake width thickness that we choose. The data I just showed you in the last slide was from about an 80 nanometer thick, so we're not anywhere near the monolayer regime. And most of the previous studies were done in monolayer, so maybe this was something interesting that interlayer coupling would be changing with this dosing. If it's in the MOS2 and we're converting a region here, we'd expect that this change in height would be somewhat proportional to the thickness of the material. You have some percentage change in the interlayer spacing, and so multiply that by the number of layers, and you'd get a thickness change that's proportional to the thickness. We looked at flakes from about 10 nanometers to hundreds of nanometers, and the change in the thickness almost overlapped perfectly. So that this change in Z for a given dose was independent of thickness across the entire range of dosing. So we thought of possibilities, what could be causing this. Possibility 1 was, okay, maybe we convert the first few layers to a metallic phase, and that acts as somewhat of a shield. It just is now a reservoir for electrons. So we can just, whatever extra dosing we put in there would just be additional, just stuck in that cap, and we wouldn't be accessing the semiconductor material below it. Or what could be happening is that it's not MOS2 related at all. This is a high energy beam of electrons. Even for our hundreds of nanometers thick MOS2, it's very likely that a lot of this beam is just passing right through the MOS2 into our substrate. And so what we did was we just had the same dosing, 1 by 1 micron regions, and we put that dosing on an MOS2 flake and one directly on the SiO2. And we can see here in the topography, we see both of those features. You can see in these high dosed regions that there's depressions not only in the MOS2, but on the silicon dioxide. And the work function changes are happening in the MOS2 as we expect, but nothing is happening in the silicon dioxide, if anything. There might be some hints of changes here. And so if we look at this change in the topographic height for the MOS2 and the silicon dioxide, they more or less agree with one another. And so we can isolate the effects in that this constriction, this topographical change is only happening in the SiO2, where the work function change is really only happening in the MOS2. And so that's great news for us. We're converting the entire thickness here. And now we want to understand that the work function change is happening in the MOS2. What can we model it? We're not looking at a single point. So this is the work function change we'd expect for each of these metallic islands, but that's not really what we're measuring. We are using an AFM tip that's around tens of nanometers wide, and our little islands are being written by a beam that's 3 nanometers wide. And so our AFM tip is, an order of magnitude bigger than the little islands that we'd be measuring. And so really we have, a curve that doesn't just look like an abrupt phase transition here that we'd expect for each island. We kind of have it smoothed out. And here we can kind of get a little picture of imagining this AFM tip sampling over the entire area. And there's some minimum, like this vertical change would be just to nucleate a single triangle here, and then as we dose more, it would expand in area. So what we're getting is, as we're dosing, the AFM is still measuring a lot of 2H phase while these islands are developing. And so this work function change would be kind of smeared out. It wouldn't be an abrupt phase transition. You can imagine that, the work function in the 2H region is smaller than this one. So the overall change in the work function would be smaller for the past the transition. And so qualitatively, at least, this data seems to agree with the measurements that we're making. I'd love to see how Jim has done those measurements of the moire interference down to 5 nanometers, because that gets us closer to resolving some of these, or we could space them out to try and resolve these islands individually. But for now, we kind of have this averaged area here, but it does seem consistent. We see that, I think this was for a thinner flake of MOS2, that we start off by reducing the work function, going a negative change, and then drastically increasing over here. For most of the dosing that we have subjected these samples to, we really haven't been able to reach the region of saturation. Does seem like we're forming these metallic islands and they're getting close to complete coverage. But for example, to write a 1 micron squared area here for the higher doses, just for one of these squares can take about 30 minutes. It's just a lot of time in the E-beam system. So unless we're doing overnight, writes, a group of these to go to another order of magnitude quickly goes from 30 minutes to several hours, just for a 1 micron squared area. So writing large area is inefficient, which is well known for a throughput issue for E-beam lithography. But we hope to kind of take this information we've gained from the KPFM and incorporate and scale down to write smaller features to do quantum wires, quantum dots that we can measure, and incorporate them into larger van der Waals header structures for use in gating, and measure the electrical properties as a result. One interesting thing that we'll note is this phase transition is reversible. You can see a flake here that has quite a few doses on it. I think we were doing 28 on this one over the full spectrum, and we were testing the stability of this. A lot of fabrication techniques for creating van der Waals header structures and patterning them into Hall bars incorporate annealing resists at like 180 degrees C. So we wanted to make sure this process would withstand that heating. And we've shown that up to about 300 C, they'll remain features on these flakes shown in the work function here. But annealing at 400 C will kind of wipe clean your slate. And so you can revert the entire flake back to the semiconducting MOS2. Basically, you've increased the work function in these metallic regions. Heating it up lets the electrons escape from that potential well and spread out, maybe escape into the environment through humidity effects, but you can kind of let those electrons at least spread out, and if not, remove them from the flake. And so you could imagine writing a pattern and erasing it, writing it again in the same flake. If anyone's unfamiliar with Villanova, we're in the suburbs of Philadelphia. We're primarily undergraduate institution, so this work was really, championed by a few undergraduates in my lab. Work closely with the Quattro nanofab facility at UPenn, where the E-beam work was done KPFM work and AFM was done at Villanova. I really have to give thanks to these two undergraduates who've worked in my lab. Peter Webb kind of started this project in last year, and he's now working at Park Systems in their East Coast office. And right now, currently have this undergraduate student who started over the summer as an REU student from not too far away, but Westchester University, who's kind of continue working on the project. And then they've been mentored by my valuable postdoc, Arash, who's been vital to the lab. And I know this was kind of a shorter story. It was kind of a one-year project, but I hope you guys are interested in seeing what has been going on there. Thanks for listening and coming today.
Awesome. Thank you so much for the talk, Professor Dietrich. We will have now a short, about 5 minutes Q&A session for any questions that anyone has for Professor Dietrich. You can ask them either in the Q&A box or in the chat, and we'll be able to get them answered for you. So we'll just wait a few minutes. All right, I do see one question. I will read it off for you, Professor. What was the pressure to erase the patterns? Was it low? The pressure of the vacuum to erase patterns?
It was a roughing pump, so 30 millitorr, nothing ultra high vacuum. That could have an effect. We tried to remove most of the oxygen from the environment, but it wasn't anything in ultra high vacuum.
They just gave you a quick thank you. So we have another question from Professor Dichalcogenides. Do you see an accelerating voltage dependence?
We haven't investigated that. There have been works that have, not necessarily for this purpose, studied the effects of electron radiation on things like graphene. In the 10 to say 100 MeV range, you don't see much damage, at least. If you start working with TEM sources, which tend to have higher accelerating voltage, you can actually start damaging the material. But we haven't varied that parameter yet. My guess would be that the material will become more transparent at higher energies. So you might have kind of an artificial effectiveness decrease because you're just going right through the material. It's kind of common for E-beam resists that just look invisible, and sometimes their dosing can change with their the higher beam energies. The other advantage might be you can focus better, and these nucleations really depend on having a focus beam. If you had a very spread out concentration of electrons, it can inhibit the nucleation of the metallic phase. But yeah, it's a great question.
Okay, awesome. And I think that just about wraps up our time for the Q&A. Thank you again, Professor Dietrich, for your time and for your presentation. We really appreciate it.
Thank you.